Quick mic check. Can everyone hear me?
Yeah, Professor.
Yes.
Okay, awesome.
Professor?
Yeah, go ahead.
All right, so with Alex, I'm having a problem where I do complete the objectives, but it's still telling me that I have a lot
Okay,
from
so
previous.
well, I'm assuming that's from your knowledge check. So if you messed up during your knowledge check, it says you need to practice these things from the previous objectives and stuff.
So even though I finished, am I deducted those points?
No, those points are not removed.
Okay, so I
As
still
long as
get
you
the
finish it by the due date, you get those points. No one can remove those points.
Okay, cool. Thanks.
Okay. Okay, so let's get started. Just a quick check. Does anyone remember if this is the slide we left off at?
Yes, it is.
Okay. So we did finish the weak acid, strong base titration. I'll take that as a yes then. Okay. So the rest of chapter 19 is going to be pretty straightforward. It's going to actually be considered easier compared to what we just did with titrations. Just for anyone who is the co-host, if you need to start recording, this is the time to do so. Okay, so we're going to first talk about the next type. We have a weak base strong acid titration. We're not going to go into detail about this, only because the same stuff is just flipped backwards. So instead of working with a weak acid strong base titration, it is a weak base strong acid titration. By the time we hit the equivalence point, it should be less than 7, because at this point, all we have is the conjugate acid to my weak base. Because at equivalence point, the amount of my base and acid are equal to each other. They cancel out. All I have left is going to be the conjugate acid of my weak base, which happens to make the solution slightly acidic. So that is why the pH is going to be below 7. And then everything applies the same way. We have a buffer region in the top right here. So that's going to happen because the concentration of my weak base plus conjugate acid are close together, not necessarily equal to 100%, maybe at that exact half equivalence point. For those of you that are taking the lab, the importance of your half equivalence point here, so this dot right here, is essentially half of this amount right here in terms of volume. So this is 40, then you're looking at 20, and whatever that pH is at that value, this is going to tell you that your pH is equal to your pKa. And the reason why we know this is because the amount of your weak base is equal to the amount of your conjugate acid. So that's why we can cancel those out when we're writing our Henderson-Hasselbalch equation. Same thing applies when we're dealing with the weak acid strong base titration. Okay, any questions before we move forward? Okay. So another example we can look at is the titrations of a polyprotic acid. Usually it's a weak polyprotic acid. So you have different steps, like you have H2SO3, you have H3PO4, things like that. It has multiple equivalence points. So in this case, because there's 2 protons here, we're looking at each H. This is the first H. It has a buffer region as well. So this is the first H, and there's this based on the second H right here. So we can kind of draw a line right here. You're going to have 2 different equivalence points, 2 different buffer regions when you're dealing with polyprotic acids. Okay, any questions? Now, if we have H3PO4, we would deal with 3 equivalence points and 3 buffer regions. Okay, now we're going to move on to the next part of our lesson. This is, I believe it should be the last part of chapter 19. Chapter 19 really consists of 3 parts: the buffers, the titrations, and then the slightly soluble ionic compounds. So how many of you remember from Chem 1 that you had certain combinations of cations and anions that were soluble or insoluble? There was a list you kind of had to memorize. Anybody remember that? Yes, no? Was it too long ago? Okay. Vaguely. All right. So even though it would say something as insoluble, right? The truth is it is actually slightly soluble. So most of it's going to stay as a precipitate and you're not really going to see it in the solution. But some of it actually changes into ions, a very, very small amount. So we're actually going to be measuring that small amount. So kind of like what we're doing with the weak acids, we're measuring that small little bit of change, a little bit of H that shows up. So once again, we will need to use the ice table because we're still dealing with equilibrium here. So if I look at example here, if I take lead and fluorine, so remember lead, if it joins with any kind of halogen, again, this goes back to Chem 1, it is going to be an insoluble compound. But the truth is it's going to be slightly soluble. So you can get a little bit of F and a little bit of lead dissolving in the solution. Most of it remains as a solid, okay? So this is a very small amount. Once again, majority of it stays here. When I write this in my equilibrium expression, if you notice, there's no point of me writing this because this is a solid. So I'm just going to go ahead and remove that completely. My new value here can be written like this, okay? So my QSP is just simply the lead times the fluorine. And then the fluorine has 2 here because we have 2 fluorines here. Any questions? Okay. Now, when we're dealing with this, once again, the terms QSP, KSP, interchangeable. One is your reaction quotient, and then the other one is your value at equilibrium, okay? QSP is always trying to strive to become KSP. So we're not doing anything different. We're doing the same exact stuff. It's just that we now add in a little subscript to it, which is referring to the solubility product. That's what your SP stands for. Okay, any questions so far? Okay. So with that said, the best way we can go about this is any kind of ion that I'm looking at. I'm going to give you just NaCl. This is a very simple one. It's a 1-to-1 ratio, right? If I had MgCl2, this is where we need to account for that 2. That 2 essentially will become 2 chlorines, okay? And then we have 1 magnesium. So when I'm writing this, the charge is still there, right? This is essentially how many chlorines I have. So that's why that number matters. Does that make sense to everyone so far? The number of chlorines you have here becomes your coefficient, which becomes your exponents. If you're having any trouble with this. Another example would be AlCl3. So we would apply the same format here. Okay. Now, with that said, this is actually going to be the easiest ice table you ever use. And we're going to talk about that in a little bit. For the time being, I want you to simply just write down the ion product expressions. So in other words, I want you to break this into their different ions that are present. Okay. I'll give you about a minute or 2 to work on this. It's pretty straightforward. Okay, does anyone else still need more time with just writing down the ion product expressions? So kind of like my QSP in the process. Okay, so we're just going to go ahead and move forward then. So really straightforward. I simply just have to separate this into their ions. I know magnesium is a 2+ charge. I put CO3 together. That's my polyatomic ion. It is 2-. This is something that you should have learned back then. There are set groups of ions that are called polyatomic ions. That means They are covalently bonded together, but then they also work together with ion functions. Okay, so we set up these three. Pretty straightforward, nothing different. For your equilibrium expression, same exact situation. I plug them in, I get UKSP. Anytime you have a coefficient, that must end up as your exponents. Any questions about just this part here? No questions? Okay. So even though this one's probably going to be the least common, you won't really see this as often. You're going to see more of the very basic ones. I'm just going to simply use two symbols, okay? X and Y, a 1-to-1 ratio. So it's not bad. You just have your X over here, and then you have your Y over here, okay? And then the other one happens to be like X, Y with a 2. So then you have your X here, you have your Y here, and then that is squared, because that 2 eventually changes into X plus 2Y, okay? And then you also have the occasional X, Y, 3. Same concept here. You have your X there, you have your Y, and then that's to the third, okay? Any questions? Okay. All right, so let's continue. I'm assuming you have already copied this down. So this one requires a little bit of math conversion. So I'm just gonna have you, actually, I'm just gonna run through this one with you real quick. You see it says grams per 100 milliliters of solution, right? What do I want my concentration to be in? Or what do I want my molarity to be in? What are my units? It is capital M, but what are the units? Not kilograms over liters. Moles over liters. So to clarify, remember, when you were referring to the amount that is actually there, you call it moles. If you're writing the amount that is there, like in terms of units, you write it as moles. This is just to clarify. I'm saying that there are this many moles present, or that there are 3 moles when I'm actually measuring it. So that's the difference between MOLES and MOLS. Okay, so with that said, this is in grams per 100 milliliters. I want to change this into moles per liter. So I need to change the first part to moles, second part into liters. Okay. All right. Any questions before we do this? Okay. Again, the only thing we are doing is simply trying to figure out our KSP. My KSP is of the lead and F2. Now, the thing is, obviously, I don't have that on its own. I have to mix 2 different chemicals together. This happens to have lead sulfate, and this happens to have, I'm sorry, I'm thinking about this completely wrong. So the first one is just simply finding the KSP based on the information that you have. You need to change this into moles per liter. And the second one, same exact thing. It's just 2 different problems, moles per liter. It's given to you as grams per liter. So we need to update that, and then we can find our KSP. Okay, so let's go through both of these. I'll go through this with you so it's a little easier. In the very beginning, we know the setup is like this. This is our equation. This thing is insoluble. Some of it comes out, so I can set it up. My equation looks like this. Happens to be a 1-to-1 ratio. Lead is 2 plus, SO4 is 2 minus, so it's just 1-to-1 ratio. Okay. When I plug this in, I need to change grams per milliliter into moles per liter. I set it up in the correct ratios, do all of my dimensional analysis setup, do molar mass to get the value of moles, and then go ahead and change it to liters. So this is what I end up with. Any questions on getting up to this step here? Anyone confused in how I got to here? Either of these two. If you're confused, let me know. Okay. So with that said, we're going to apply a little bit of stoichiometry. If I wanted to separate these two, this much lead and this much SO4, I can simply say that 1 mole of PB, 1 mole of this thing will make 1 mole of PB and 1 mole of SO4. So it's a 1-to-1 ratio. Okay. So the concentration of either one of these is this, which is the same stuff that you started with. So just like if I had 1 NaCl, this really is 1 Na and 1 Cl. So that's exactly what we're kind of saying here. Does that make sense so far? Anyone confused? Okay. Yes, it is part of the question. That's your molar mass of lead sulfate. It was mentioned in the previous slide. Does that answer your question? Okay. But once we get to here, I can actually plug in the values of this one and this one. This is the number that I've been given, right? 1.4 times 10 to the negative 4. And since it's the same thing, I simply just square this entire thing, and this is what I get from my value of KSP. Any questions on how to get the value of KSP based on what we have here? Okay. Does anyone need time to copy this down before I move forward?
That's a question.
Sure.
So if it were just example for if SO4 had 2 in front of it, we would have to multiply it by 2 in order to get the concentration
Yes.
for.
So essentially this would just become, so these wouldn't be equal to each other, right? This one
Okay.
right here would just be 2 times 1.4 times
Got it.
10 to the negative 4. Okay.
Okay.
Then essentially you would have that first one, 1.4. I'm not going to write the 10 to the negative 4. And then this one will be whatever double that is. So 2.8.
Yeah.
And you still
Okay.
need to include the squared, right? So in this case, if this is 2, that would mean that this is now 2. So I need to put a 2 here.
Got it.
Get
Okay.
it?
Yeah.
Okay.
Oh, so we are multiplying with 2 and also squaring it twice.
So
Oh.
both for the KSP expression and for inside of the itself.
Oh, okay. Got it.
Okay.
Okay. Thank
All right. So once again, for the last step, all I did was just write this expression down. These two are just whatever this value is here. So that's why there is a squared here. They're just simply taking this times itself. That is how we get this number here. Does that answer the question of the person who just asked on the chat? Okay. All right, so let's take a look at the next one. This is exactly the example we were talking about. If you notice, there's a 2F here, right? So I convert grams per liters into moles per liters. This part is just your basic math, okay? So if you're having trouble with this, let me know. We can practice that. So you should end up with this concentration of the entire thing. And stoichiometry says that if I have 1 mole of the entire thing, I should have 1 mole of this, but 2 moles of my F minus. So if it's 2.6, it should be just 2.6. This one is 2 times 2.6. So this is the new concentration of all of my F minus present. Does this make sense so far? Remember, this goes back to stoichiometry. If you're having trouble with this, let me know. Okay. So with that said, I'm going to plug in these new concentration values into my equilibrium expression. So it's 2.6 times 5.2. Remember, I am also squaring this because now this squared comes from that 2. So I must include that there. Okay. So once again, this value times double of the amount squared gives me my answer. Okay. Any questions about this so far? Okay. So you'll start to notice a trend here. If I'm writing my KSP, if I'm just using the letter X, okay, whatever my concentration is, this is just X molarity for the concentration. And if this happens to be a 1-to-1 ratio, such as like NaCl, right, this would just be your X times your X. So the square root of this KSP would give you your answer, okay? If I had, just as we mentioned before, MgCl2, right, this would just become KSP is equal to your X, and this one is not X anymore, it's 2X, twice the amount, and then it is squared. So that is how we go ahead and solve it for our value of X. And then it goes onwards and onwards and stuff like that. If I did, once again, AlCl3, this would just be your X, this would be 3X, and then this would be cubed. Any questions? Okay. So with that said, I want you to go ahead and calculate the molar solubility of this thing using the same information that we had before. You're just given one less step, essentially, okay? You're just given KSP. I want you to go ahead and work backwards this time. So use this to find your X. Give you a few seconds with it. A minute. Okay, does anyone else still need more time with this problem? Or you don't know where to start? Okay, did anyone else get the same answer or did you get a different answer? Okay, so let's go through this, okay? I set this up the same as I would an ice table normally, right? I am trying to solve for one of these components, okay? So instead of using the letter X, I'm going to use the letter S to represent solubility. So I'm using the letter S. I'm just changing that letter, okay? My writing is going to be the same format. So this is our setup right here. I have 2 hydroxides, right? So this becomes a 2. Everyone see where I got that? Take your silence as a yes. So I set it up. I don't care about this solid here. I'm going to leave that completely blank. Okay. I start with none of these because remember, it's barely soluble. So most of it is just going to be 0. So when it does change, I should have some amount of it equal to the concentration, whatever that concentration was, right? And then this is twice the amount. So twice the concentration. This is just your stoichiometry. So I get S and 2S. So I'm going to plug these in right here. S and 2S. Okay. Then I remember I still have to include that square. So this is S times 2S squared. If you were to simply just put it all together, it would just be 4S cubed. Okay, because you would solve for this first. That gives you essentially 4S squared times this. It will give you 4S cubed. And so 4S cubed is equal to this. I'm just going to algebraically solve it, doing the cube root of this and then dividing that by 4. And I get this number right here. This is my S. If you want to refer to it as X, you can refer to it as X. Any questions so far? Okay. Now remember, you can interchange between your KSP and your solubility. They are similarly related. As this one increases, the other one should also go up. Not exactly the same ratio, but it should go up as well, depending on our setup. Is it going to be a 4S cubed, or is it going to be S squared, or is it going to be something else completely different? Okay. So those are things to keep in mind of. All right. Does anyone else still need time to copy this down before I move forward? All right. So going back to what I just mentioned, the higher the KSP value, the greater our solubility, the higher that S value, right? But it also depends on how many ions I have. So I can just simply say, if I looked at this group right here, only at this group down here, for anything that has 3 ions, it could be 2 cations, 1 anion, or 1 cation, 2 anions, any combination of this, as long as my KSP goes up, my solubility should also go up. So in this case, this has a higher KSP, right? That means this should have a higher solubility in terms of ratios there. But I cannot relate these and these. They don't go directly equally. So if I can't just say, let's say this one right here, oh, I'm looking at this KSP, I'm looking at this value right here. This has a lower KSP, so it must have a lower solubility, and that's not necessarily true. Okay? So you see how this one has a higher KSP, but its solubility is actually lower than this one right here. So it cannot relate if there are a different number of ions. Does that make sense to everyone so far? Yes, no? A good way to kind of figure out how to find out my solubility, if it's just 2 ions here, remember KSP is equal to the 1 times 1. So this is essentially just S times S. Okay, so that simply means that KSP is equal to S squared. So this is my S right here. So this is just the square root of this. So all of these are the square root of that previous one. If you don't believe me, try it out. Once again, this is just the square root of each one of these. That will give you the answer for the solubility here. Okay, but for my cube root here, of my 3 ions, I have to do something different. Remember, it is essentially S times 2S squared. Okay, and to solve this, this comes out to about, yeah, so this is a 1-to-1 ratio of the ions for cation and anion for the squared. That's correct. For this one, it is going to be cube root, so 4S cube root. So what's actually happening here is I'm going to have to cube root this and divide this by 4. So if you're not certain what the answer is, when you divide this by 4 and cube root it, you should get these answers here. And that's the same thing across the board for each one of these. Okay. Now, in reality, the most common you're going to see is either going to be a 2-ion one or a 3-ion one. Only these combinations. There are 4-ion ones. Now, that gets more complicated because when I'm trying to do this, essentially is your S, and then here you have your 3S, and that's cubed. So that becomes more complicated because by the time we're done with this, this becomes 27S cubed times another S. So that actually comes out to a total of 20S4. So I don't want to go ahead and use this to solve for my S. It's going to be a big pain, but essentially the same format. I take whatever my KSP is at that moment, divided by 27, and then do the square root of the 4, okay? Any questions? All right. So the reason why we do this is also because it's called the common ion effect or common ion solubility. So it's very similar to the common ion effect we mentioned earlier. So we're dealing with the same exact stuff, okay? This should either, if for whatever reason, I don't produce, I guess it's not gonna stay as solubility wise, right? It's gonna return to being solid. It's gonna produce a precipitate, but it's the same ion. Okay. That's the main thing between these. They have similar ions on both sides. Anyone have any questions before I move forward? Okay. So let's talk about the term precipitate. Precipitate is when something happens or a solid forms, it doesn't dissolve or will not dissolve into the liquid. Okay. So only in one scenario out of all of these here is it going to produce a precipitate. So remember we learned about solutions. We had saturated, unsaturated, supersaturated, right? In our supersaturated solution, if you remember that, and when this is unstable, right? So it's already past the solubility point. So it has more dissolved in it than it should. So if we disturb this at any point, it will immediately turn back into solid. In other words, it will precipitate. Okay. So out of all these scenarios, only this one right here. When QSP is greater than KSP, a precipitate will form. So I'm going to go ahead and just write this as an example. I have some kind of solid here. It breaks into two aqueous solutions, okay, or two aqueous ions. When QSP is greater than KSP, which way does this reaction shift? Left or right? It will shift to the left. What do I have on the left side? What type of substance do I have on the left side? Well, it is a reactant, yes. What phase is it in? It is a solid. It is essentially, QSP is, if it's greater than KSP, oh, sorry, QSP is greater than KSP, it's going to shift to the left. When it shifts to the left, it is making a solid. That is why a precipitate forms. In all other scenarios, there's no shift, right? Or the shift is to the right, where I am essentially not making any solids. So this is why the precipitate forms. Okay. So this kind of ties back in a little bit with the solutions that we learned in terms of saturated, unsaturated, and supersaturated. Okay, so looking at the problem here, I want you to give this a try. You're given this concentration and this concentration. Obviously, I want you to focus on this, okay? Out of all these combinations, when calcium is joined with fluorine, this is going to form a solid. Okay, so it's going to form a precipitate in that sense because we have this equation here. So this is an insoluble compound. It's essentially slightly soluble. I want you to apply everything here and then tell me if a precipitate will form. This is your standard KSP value given to you here. You are essentially calculating your QSP. So give you about a minute or two to just get this started and try it out. Okay, is anyone having trouble starting this one? Okay, does anyone just need more time? Okay, so we're just gonna get started with this then. So you're given these values right here. You need to go ahead and find the moles of each one, okay? So then you can essentially find out how much you have in total and you can interact with them with each other. So these two are both soluble in their own regards, but when they join together, Ca2 plus and F minus joined together is insoluble. So this is our focus, okay? I put everything together in terms of my concentration, how much calcium I have in general, and then how much fluorine I have in general, okay? So then I combine the two of these together using my QSP, and this is what I should get. This is my QSP. Anyone have any questions on how I got to here? This is just the concentration of, or the moles, molarity of my F minus and my Ca2 plus. No questions? Okay. So in this scenario, it tells me that QSP is greater than KSP. So that means it will form a precipitate. So most of it will reform into a solid, while the rest, the little bit left, stays as a liquid. Okay, any questions? Does anyone need time to copy this? Anyone confused about what to do here? Need time to copy it? Okay. Okay, does anyone else still need time to copy this down?
Professor,
Yep.
don't you have to multiply 2 with F?
You technically did. So if we look here, right? It already tells you how much you had. So I guess you didn't really have to because it's not telling you the overall concentration. So it's not telling you that you have CaF2, not giving you a concentration of that. In this scenario, then you have to multiply that too. It's just telling you this is how much F minus you have in general.
Oh,
You get it?
and but
And it's
is
coming
it-
from two different sources. So
Mm.
this is the F minus coming from the source with NaF. So you don't have any other source of F. That's why it's telling you that this is how much you have.
oh, okay. But in the previous slide, we find the QSP for CaF2.
So
Calcium
to clarify,
fluoride.
okay? If I said to you, I'm just gonna make this up in front of you right now, okay? I have 5 molar CaF2. Stoichiometry says that I should have 5 molar of this, and because this is F2, that's essentially 2 F minus, right? That means I should have 10 molarity of F minus. Does that make sense?
Yeah.
Okay, that's if I gave you this. I didn't give you this, right? I gave you this and this. That makes
Oh,
sense?
yeah, because you started with that.
Yeah, so I don't care about this part and I don't care about this part because they are soluble. I care about how much calcium I have and I just put it in here. And I care about how much fluorine I have and I just put it in there. That makes sense?
Okay.
I still need
Yeah,
to
yeah.
include this squared here, which is why I have that there. And so that's how I got this number here. But I'm not doing stoichiometry directly from here.
Okay.
Okay. So it
Yeah.
depends on where your source is. If it just says you have this much fluorine in general, then that's the number you have.
So what if sodium fluoride was replaced with calcium difluoride? Then we would have
Well, if you replace calcium
multiplied.
fluoride, then I need to account for the calcium too. So I need to increase this number as well. Okay.
Okay.
But usually, yeah, then if this was F2 or anything that has a 2 in it, then you need to account for that amount.
Okay. Okay.
So
Yeah,
just
makes-
like NaOH, right? It's just 1 to 1. If I had
Mhm.
said calcium hydroxide, right? I need to account for that every 1 molar of this, I should have 2 molar of my OH minus.
got it.
Okay.
Yep.
It just happens to mention 1, so we don't need to do anything else with it. This is just a concentration. Okay. Anyone else still need time with this? Okay. Some ending reminders. Henderson-Hasselbalch equation is only meant for buffers. Make sure you do not forget that. Titrations that you're doing in this class is just a series of ice tables and a bunch of dilutions. M1 V1 equals M2 V2. So if you can see it that way, it's pretty easy. Just always look at what is in my flask or beaker, what has mixed, what do I start with, what are they, when they mix, what do I have left, and what does it react with. Calculating solubility in KSP is the easiest version of ice table that we deal with. As long as you change all those to correct ratios, you are good to go. Make sure your algebra is good. And the only time that we will form a precipitate is when the QSP is greater than KSP. So for this topic here, even though it's a lot of information, especially in titrations, it really is only a few things, 3 or 4 different things that we're going to focus on. Okay. Now, a question for everyone here. Why did the weak acid and its conjugate base go to the gym? To get buffer. Okay, so we're going to go ahead and transition. Give me 1 second while I set up the next one. Okay. I do come up with some of them and other ones I find online. So does a mixture. Okay, so we're going to get started with chapter 20. We are a little bit ahead of our schedule, and that's okay. So chapter 20 focuses on thermodynamics, kind of like the question of why things work the way they do. So a lot of other teachers, if they are physical chemists, right, they prefer to teach thermodynamics first because they want to teach you the why before they teach you about the rest of the stuff. Okay, so we're going to learn about a term called spontaneous here. So the term spontaneous isn't the same spontaneous that you think of. It doesn't mean that someone just suddenly wants to do something. It's not based on that. The term spontaneous here means it happens and occurs without extra input of energy. So it's going to keep going and it's going to start on its own. I don't need to do anything to make it happen. Okay. In comparison, non-spontaneous requires a constant supply of energy. So I'm going to give you some examples just to make sure you understand it. How many of you have your own room? Okay. Over time in your room, what happens as you are living in it? Living room counts too. If it's your room and no one else goes there, becomes messy, right? Did you have to put any energy in order to get your room to be messy? No, right? Things happen naturally. Even if you kept your room as clean as possible, you know, you have dead skin cells, it gets dusty, hair falls on the floor, things like that. It gets messy on its own. Okay. So a messy room is essentially a spontaneous reaction. What about cleaning your room? Does that require energy? So if it requires energy, that is a non-spontaneous reaction. So to clean your room, you need to put in work. You need to put in energy. Okay. So that's the difference between a spontaneous and a non-spontaneous reaction, in case you were confused about it. Okay. So we're going to talk a little bit about the laws of thermodynamics. We're going to focus on 3 of them. So this is the category where it branches slightly into physics, including when we spoke about nuclear. This is when we slightly branch into physics. For the first law of thermodynamics, the only thing you have to remember about this is that the energy in the universe is constant. So I can change the forms of energy, but I cannot create or destroy it. So an example I'd give you, if I ate food, that is me digesting the food becomes chemical energy. I'm using it in my body. And over time, we excrete it in the form of matter, or we excrete the energy in different other forms. Just breathing, you're using energy, using thermal energy. So if someone ever asks you, like, are you exercising? You could tell them you are breathing. That is considered part of your exercise. You're burning calories just by breathing. Okay, so once again, energy, it cannot be created or destroyed. It is only changed from one form to the other. So the energy of the universe is constant. And we're going to go ahead and try to see which of our laws of thermodynamics tells us whether something is spontaneous or not. And this law does not tell me anything about spontaneity. So it doesn't tell me anything if it's spontaneous or not. It simply just tells me the energy in the universe does not change. There's two other terms I want you to be familiar with: system and surrounding. Okay, so if I'm looking at an object, whatever this object is here, this is my system. You can also call this your reaction, but this is just simply known as system. Everything else outside of that system is known as your surrounding. Okay, so if I'm holding up a cup of coffee, I'm looking at that cup of coffee. That cup of coffee is my system. Everything else outside of that cup of coffee is the surrounding. People looking at it, people standing there, the air around it, anything else is considered the surrounding. So we have mainly two terms, system and surrounding. The two of these added together always make up our universe. Okay, any questions before I continue? All right. So another thing that we mentioned is also delta H. How many of you remember exothermic and endothermic reactions? Okay, what does it mean to be exothermic? So I see heat loss, release heat, release energy. Those are all correct, okay? Endothermic means it is absorbing energy. So it also depends on our perspective. So if I look at this object and I'm referring to it as a system, and I said this is undergoing exothermic reaction, is it losing or gaining heat? So this should be releasing heat, okay? So heat should be leaving it. So who is receiving that heat? Who is receiving the energy? The surrounding, okay? So if this is undergoing exothermic reactions, what is the surrounding undergoing? Endothermic reaction, okay? So heat is always transferred from one place to the other. We're not losing this heat. It's not really gone, right? It goes from system to surrounding. So in terms of the universe, have I lost any heat? Or have I gained any heat? No, right? So this is our first law. It says heat is, we're looking at heat energy is just being transferred from one place to the other, one form to the other. It is still all in the same universe. It has not left that universe. Okay, so with that said, delta H, when it is positive, it is endothermic, negative, it is exothermic. Usually this refers to a system that we're looking at, but sometimes it could refer to the surrounding. For both of these scenarios, both of them can be spontaneous. You can have a spontaneous exothermic reaction or a spontaneous endothermic reaction. The best examples are when we are looking at a scenario right here. If I look at a piece of ice, okay? If I place this ice cube on outside in a sunny day, do I need to do anything to it to make it melt? If I don't need to do anything to it, it is considered spontaneous. If I put a cup of water in a freezer, do I need to do anything to it in order to make it freeze? And the answer is no, right? So in both scenarios, if you look at it, if this is going to be the system here, right? When this is outside on a sunny day, it is essentially absorbing the heat. So this is undergoing an endothermic reaction. And it can be spontaneous. If I have an object that is out in a freezer, essentially what's happening here is the heat from here is leaving. So that is an exothermic reaction, and that can also be spontaneous, depending on the place that it is at. So spontaneity is not determined by exothermic or endothermic reaction. So delta H cannot determine that. Some examples here. This is just an example of showing you that endothermic reactions can be spontaneous. Okay. So the one thing that will determine whether or not something is spontaneous or not is an increase in the freedom of particle motion. So you may want to write this down. Increase in the freedom of particle motion or freedom of motion of particles. If particles are free to move out away from each other and have the ability to move around freely, and the more easily it can move around freely, the more likely it will undergo spontaneous reactions. And then the less likely that it will undergo, the less freedom that it has, then the less chance of spontaneity, or no spontaneity. So I'll give you a second to copy this down. This is the main drive for whether something is spontaneous or not. Okay, does anyone else still need more time to copy this before I move forward? All right, give me a few more seconds with it.
Professor, one question.
Yeah, go ahead.
So here it says all spontaneous endothermic processes result in increase in the freedom of motion. Is it specifically for the endothermic processes, or there's something related with exothermic processes also?
It is also relatable with exothermic process. So our goal is to simply look at freedom of particle motion. That's
Okay,
kind of like the overall summary. As
okay,
long as particles can move around freely, it
Mhm.
is going to be spontaneous.
Got it. Okay, thank you.
Okay. Okay, so let's continue. Again, you don't need to go into too much detail about microstates here. The only thing you really need to know is that as we increase in the number of microstates, we are increasing the possibility or ways that energy can be dispersed. That is the only thing you really need to know about this. Okay? More ways that it can disperse means larger possibility of microstates. Very straightforward stuff. I'm not even going to ask you questions about this. Maybe one question, it's more of a concept question. Okay? As it increases, more possibility, greater chance of spontaneity, more number of microstates. That's mainly it. So what we will talk about is a term called entropy. And entropy is related to the number of microstates. Again, more microstates, higher the entropy. The term entropy refers to disorder. Once again, the term entropy refers to disorder. So this also known as randomness, also known as chaos. So we treat this as if something we can measure. Okay. Let me give you an example. Let's say you happen to cut down some small trees. Okay. And then you take those trees and you put them neatly stacked together in one area. Are you increasing in entropy or decreasing in entropy? I'm taking trees that I have cut and I'm stacking them into an area neatly piled up. I am decreasing in entropy, okay? Because entropy is a measure of disorder. So my disorder is going down because I'm neatly stacking them. Now, question for you. In nature, when a hurricane passes by and trees fly up and then they get thrown to the ground, are they neatly placed on the ground? No, right? So what does nature normally do? Nature is naturally increasing in entropy, naturally disordered. Okay. So that's something to keep in mind of. All right. So again, don't worry so much about the microstates. The term is very, very irrelevant in this scenario. Increase in entropy, more microstates. That's about it. So let's talk about the second law of thermodynamics. This ties in very well with our ability to figure out if something is spontaneous or not. Okay. So I'll give you a second to copy this down if you need to at the end. Second law of thermodynamics simply means that if the system plus the surrounding of entropy, and if that value is greater than 0, so in other words, the entropy of the universe is increasing. Okay, so in other words, the universe is getting more chaotic or more disordered, then you have a spontaneous reaction. So a spontaneous reaction will occur if it generates more disorder naturally, or more disorder in the universe. That's the best way of putting it. And our equation, again, this is just the relation between system and surrounding. The two of these added together is equal to your universe. So if the system happens to equal the surrounding, right, then this usually is the negative value. This is the positive value that makes something 0. So the system, the entropy of the universe can come out to 0 if this is positive and this is negative of equal value. But the main part is what is written right here. Once again, any spontaneous reaction that occurs will increase the entropy of the universe. So I'll give you a second to copy that down. Okay, does anyone else still need more time? All right, let's continue then. So when we talk about the energy of the universe, we once again refer to it, it remains constant. So delta E of the system plus the surrounding equals delta E of the universe. Delta H is often also associated with energy because a lot of times we focus on the value of the heat going in and out of something. Okay, so that's also the form of energy. One thing I want to point out here is that delta H can never be 0. So heat is either going to leave or enter in some form and or way. Okay, it can never be 0. Even when you're dealing with a calorimeter, that is never 100% 0 either. So it resists a lot of the change in the heat. So heat kind of gets trapped in there, but it does not actually stay at exactly 0. There's always a change in heat or change in enthalpy. So this is never going to be 0. However, the entropy can be 0. So disorder can be essentially 0. So you can essentially have no disorder. So just as I mentioned before, if this comes out to 0, right, then one of these is equal to the negative value of this, okay? So there can be a 0. Now, ideally, whenever we're dealing with a spontaneous reaction, this value is positive. Okay, any questions so far? All right.
Can you actually repeat that last part, please?
So this is always going to be positive in a spontaneous reaction. That's pretty much our previous slide. Second law of thermodynamics. Okay. Now, on to the very last law of thermodynamics. Like I mentioned, entropy can be 0. Disorder can be 0, essentially. This is usually referring to a system. So it's saying that a perfect crystal has 0 entropy at absolute 0. How many of you have heard of absolute 0? right? What happens at absolute zero, because we use Kelvin as a measurement. If you can get temperature, there's essentially no negative Kelvin, okay? The lowest temperature in existence in the universe would be 0 Kelvin. Now, even as of this moment, scientists have never reached exactly 0 Kelvin. We've gotten things very close to it. I think we've gotten it to a fraction of a second, somewhere like maybe 1 out of 200 of a second, not a second, of a degree. So it's essentially 0.00 something Kelvin. So we've gotten it down to that level to essentially see what happens. When you get something to at exactly 0 Kelvin, this is, again, theoretical. If you get it there, all molecular life stops. That means molecules don't even vibrate, they stop moving completely. And we're looking at the atomic level, things don't move at all anymore. So it's kind of like saying it's a true frozen state. Okay. We go back into microstates again. If we only have one microstate, so in other words, there's can only be one possibility. That was where we put in ln of 1. Doesn't matter what our constant is here because this essentially just becomes 0. So entropy is equal to 0 if there's only one microstate. But again, microstates, very minor. Don't worry so much about it. Okay. That's great. I don't know how true that is. Okay, so moving on to standard molar entropies. Okay. You're going to see this little symbol right here. That refers to standard values. Standard values here mean that if I'm looking at gases, it's 1 atm. Concentrations, it's 1 molar. If it is a pure substance, I can pretty much ignore solids and liquids. They don't get included. Okay, so these are very important terms. Anytime you see this, it refers to the standard state. Standard state means 1 atm for gases. These are set values. Okay. Does anyone need time to copy this down?
Yes.
Okay. Okay, so let's continue. So we're going to talk about things that actually do affect our entropy. So one of them is dependent on temperature. Okay. If we go and define temperature, it is the average, it's a measure of the average kinetic energy. Higher the temperature, faster things move, and the more energy that is present. So entropy should increase along with temperature. So if things are moving faster and they're colliding with each other, more kinetic energy, there is more randomness, more movement, and more freedom of particle motion. It also depends on the physical state. If things are in the solid phase, they tend to be closer together. So the entropy is on the lower side, it is more ordered. As it gets to the gas phase, it is more spread apart, more freedom of particle motion, greater the entropy. The formation of a solution affects our entropy. In most cases, if you are making a solution, such as the example of solids mixed with liquids, right? In most cases, it should increase in entropy because there's more movement of the ions. There are some exceptions where certain liquids combine together, certain combinations of the interactions of your, I don't know, your ions and your water or whatever it is, may actually increase or decrease entropy. For most cases, it should increase entropy. And it also depends on the atomic size and molecular complexity. The more complex it is, the more disorder and chaos there is. The larger it is, same exact thing, because there's more interaction between all of the electrons that are present in terms of all the bonds. Okay, does anyone else still need time to copy this? We're going to go into a little detail of each one of these. Okay. Does anyone else still need more time before I move forward? Okay. So looking at this example here, higher the temperature means more freedom of particle motion, more microstates, more movement, more energy when they crash into each other, more kinetic energy. It is an increase in entropy. Remember, entropy is the measure of disorder. Okay. So it's related to our spontaneity, but the object itself or the system that I'm looking at doesn't necessarily have to have a positive entropy. As long as the entropy of the universe increases, then it is spontaneous. Okay, again, same thing. You don't need to know too much about this in terms of microstates. Just know that higher the temperature, increase in entropy. And another example of the same stuff. When we look at phase changes, again, solids tend to stay closer together. They don't really move as much. So if you go into the form of gases, it tends to have a lot more entropy because gases spread everywhere. And in terms of solutions, it depends on the interaction of your whatever two reactants that you have. But generally speaking, it should be an increase in entropy in most cases. So in ethanol and water, there is an increase as well. It's a very small increase. So it disrupts the hydrogen bonds that you normally have and adds in the other hydrogen bonds with ethanol. There is a slight increase in disorder, even though it is very small. Okay, once again, entropy and atomic size, the larger it is, greater the entropy, the more complex it is, greater the entropy, larger the radius, same exact situation. Okay, more possibility of things happening. In terms of if you ever decide to take physical chemistry or quantum mechanics, you're going to realize that when you're dealing with electrons, if you're dealing with just one electron, it's easy to kind of manage it and look at it. If you have two electrons, they have different interactions. They kind of repel each other. They kind of attract to each other. A lot of things are moving at the same time. So when you have things that get more complicated, the larger the atom, the more complex the compound is, the more things are happening, more entropy. Same thing with structure. Again, more complex, higher entropy. Very straightforward stuff, okay? An important one right here, we have graphite and diamond. So they each have a set entropy value here, okay? Diamond, they're a little more ordered together, so their entropy is lower than graphite. All right, any questions? Okay. Now I want you to go ahead and take some time, look through this entire list, and then tell me either the left side or right side, which one of these is going to have a higher entropy, okay? And we're going to assume that these all have constant temperatures with the exception of E because they're giving you a different temperature. So temperature is not changing in any of these except for this one right here. So I'll give you a few seconds to look through it. And then you're either going to write left side or right side, depending on the letter with higher entropy. Again, we're not just trying to answer letter E here. Do it for all of these here, and then we'll go through it together. Okay, so let's go through this. For the very first one, you have 1 mole of SO2 gas or 1 mole of SO3 gas. Which one has higher entropy? The right side, okay, more complex. So we're going to circle that. Next one, carbon dioxide, solid or gas? Gas form should have higher entropy. 3 moles of O2 or 2 moles of O3? Left or right? Okay, the answer is actually going to be the left side. There are more moles of this, even though this in terms of complexity is more complex on the right side. There are more of these here. So there's going to be more interactions and more randomness. Okay. Next one, solid or aqueous solution? It is the aqueous solution, more freedom to move around. This is, you have the K plus and the Br minus floating in water. They are moving around. And then for the temperature one, someone mentioned earlier, it was 23 degrees Celsius. What about our last one? Left or right? The answer is right side. The chlorine, if you think about it, fluorine usually just has, if you look at the electron configuration, it's essentially 2, 7, right? So this one is 2, 8, 7. Okay, so you have more rings here. More rings means more interaction between the different levels of electrons. It's just more complex in general. Okay. All right. So we'll go through all this. We just went through all this, so we don't need to copy it. So I want you to try it with this one right here. It's either going to be the left side or right side in terms of pressure. Okay. Go ahead and either type in the chat, left side or right side, whichever one you believe will have higher entropy, higher disorder. Okay. Everyone that typed left got it wrong. So the answer is going to be the right side. Okay. And let's talk about why. So let's relate pressure and volume. As pressure goes up, what happens to the volume? Not a trick question here. Goes down, okay? So I want you to imagine this scenario. You are babysitting. You have 10 kids with you. They're all 5-year-olds. They're all in a classroom with you, okay? We'll say a normal classroom, recitation classroom size, maybe 30 kids can fit in that classroom, okay? They're in that classroom with you. Can you manage babysitting them in that classroom?
Yes.
Some of you might be able to, right? Some of you are probably like, no, I don't want to even try that. Now, what if you had those same 10 kids, but instead of in the classroom, you were at the mall? No, right? That just becomes too much trouble because of all the space you have. So same concept here. Remember, pressure is related to volume. This has a greater volume. What do gases do when they have plenty of volume? They spread around. They run around, kind of like a bunch of 5-year-olds, right? They will spread out as far as they can, run to every corner they can reach. Again, that means more disorder, more chaos, more randomness. Okay? So molecules work the same way as 5-year-olds. Okay, so let's talk a little bit about the changes in the system. When you see reaction, it's the same thing as if I'm referring to the system. And it's made up of 2 things. You see the term delta. What does delta mean? Change, right? Change between the products minus the reactants. So whatever your products are minus your reactants is going to equal your change. So a lot of times you're going to see a list of things here later on. You won't have your delta S written to you directly. You need to calculate your delta S by looking at all the values of your products minus all the values of your reactants to give you that change. Okay, and you need to include your coefficients for those as well. So later on, we're going to do some practice problems with that, and that will come up. Everything we've covered so far has all just been concept. Chapter 20 is very concept heavy. Okay, at the very end, we have some math problems, but most of it is concept heavy. Okay, so looking at this example here, I can either, depends on what I am trying to produce here. So if I look at this first example here, right, it depends on the change in the number of moles of gas. Okay, as I shift from left to right, have I increased in the number of moles of gas here? Yes or no? I have 1 mole, 1 mole. This is still 2. So essentially 2 moles, right? So I haven't really changed the number of moles of gas, but this has gotten more complex. Okay, so delta S is positive in that sense. What about in this second scenario here? Synthesis of ammonia. Am I increasing in entropy or decreasing in entropy? And yes, it says negative there, so you know what it is. That's because I'm going from 4 moles to 2 moles. So I'm compacting them together. I'm forcing it together. Okay. Anytime you have more freedom of particle motion, delta S is increasing. So if you look at the bottom example here, we go from a triangle ring, right? You learn more about this when you get to orgo. We break it apart with some heat into a single bond and a double bond gas. And at this point, there is more freedom of particle motion between any one of these here. So that means delta S is going to be positive. Any questions? Okay. So just as I mentioned, if you change something with the system, you also kind of indirectly affect the surrounding. So if we're looking at heat here, as I am, if you look here, this is negative, right? This is your delta H. So Q is the same thing as if I'm looking at heat. So my delta H is negative. Is that exothermic or endothermic? Not a trick question, right? It's written right here. So delta H is negative. We have exothermic. If the system is essentially losing heat, it is going towards the surrounding. So this is becoming more positive. And also as a response, the disorder of the surrounding is also increasing. Because if I look at the box here, this is my system. Heat is leaving. It is going to my surrounding. So the surrounding here is getting hotter. Okay, the heat is increasing here. That also means that particles are moving more faster in the outside area. So my delta S surrounding is going to be positive. So we can relate heat with our delta S surrounding, whether it is positive or negative, because this is either giving us heat from the system or removing heat from the system. So with that said, we can go ahead and expand and write this equation down. Our delta S surrounding is related to mainly the exothermic or endothermic reaction. So my delta H, in other words, the change in enthalpy. And it's also affected by temperature to a degree. So I'll give you a second to copy this down. This is a very important equation. Okay, does anyone else still need more time to copy this down? All right, let's continue. So we can also relate delta S to our equilibrium expression. When we say a system has reached equilibrium, it's not going to move in the forward direction or reverse reaction. Neither of these is spontaneous. So I can essentially say that the delta S of the universe is equal to 0. Okay. If delta S of the universe is positive, that means I am shifting in the forward direction. So when I say something is spontaneous, okay, I am saying that it will move forward on its own. In other words, we're always looking at the forward reaction. Okay. Non-spontaneous usually means it is moving in the reverse reaction. Because if it's spontaneous in one direction, it's usually non-spontaneous in the other direction. And then if it happens to be at equilibrium, this is equal to 0. Okay, any questions before I move forward? All right. So let's talk about 4 possible scenarios, okay? Now, in order to be spontaneous, anything that needs to be spontaneous, I need this to be positive, okay? Same thing here. Now, the most obvious one is if I look at the scenario here, it says that I have an exothermic reaction. Remember, a relationship between exothermic means that delta H is negative. If this is negative, the delta S of my surrounding, according to the equation you had before, should be positive, opposite signs, okay? Because if heat is leaving the actual system, it is going to my surrounding, causing my surrounding to become more disordered. So that is going to generate a positive here. If the reaction itself is a spontaneous, an increase in entropy, in other words, there's going to be an increase in disorder, 2 positives added together, I get a positive here for my delta S of the universe. That means this reaction is spontaneous. Okay. Also in the scenario where I have an exothermic reaction, my delta S surrounding is still positive. So this is the scenario where my reaction itself can produce an order situation. So in other words, it is negative. So it's not going to produce disorder, it's going to produce order. But enough heat is traveling from the system itself to the surrounding that it's going to essentially make this positive. And this positive is greater than the negative that's here. So my overall comes out to be positive. So then this can also be spontaneous. Any questions? Okay. With that said, I have another scenario for you here. This is where we say that the system itself is going to produce an entropy situation. So in other words, it's going to be disordered, right? But this is an endothermic reaction. That means I'm taking heat away from the surrounding into the system. So this is going to be a negative value. I want this negative to be small enough that this remains positive, the delta S of the universe. So this can still be a spontaneous reaction if my delta S of the surrounding is small enough compared to the delta S of my system. Does this kind of make sense to everyone so far? And in the very last scenario, if my delta S system, right, if the entropy is actually decreasing in the system itself, and it was an endothermic reaction, so the delta S of the surrounding is also negative, then my delta S of the universe can never be positive. It's going to be negative. So this will never be spontaneous. This is the 4th category that we don't have listed here. Okay. So you may be very confused because I just named a lot of the same things. You see the word delta S, and then I mentioned the word spontaneous, and then I mentioned the word entropy, okay? So it gets all a little bit confusing, and then we also mentioned endothermic and exothermic. So we have a simple way of doing all of this together. This is known as the Gibbs free energy. So I want you to copy down this equation right here, okay? This is all for our system. So we're looking at delta G, delta H, and delta S of the system only. I'm not going to focus on surrounding. I don't care about that. The system itself here will tell me everything I need, whether this reaction will be spontaneous or non-spontaneous or at equilibrium. So I'm keeping everything inside of just the system. And then we're going to look at it that way. So I'll give you some time to copy it, then we'll talk about each piece. Okay, does anyone else still need more time to copy this down? All right. So really quickly for this is known as our free energy change, okay? So remember what we mentioned before, freedom of particle motion. If it is given the ability to move more freely, have more freedom, right? Then it will be essentially a spontaneous reaction, okay? In this scenario here, if this change comes out to be negative, that means we've used up that free energy, used up that freedom that we have. Then it tells me that the reaction is going to be spontaneous. If in the end, I've actually not used up that freedom and it becomes a positive value, right? Then it'll be a non-spontaneous reaction, okay? A simple way of looking at this, also, this is your either exothermic or endothermic. That will determine the sign. It's either going to be positive or negative. And then whether or not this is going to be an increase or decrease in entropy of just the system. So everything here, we're focusing on system, and we're going to look at different possible scenarios, okay? There's 4 different possible scenarios. So I can either have delta H and delta S both be positive, both be negative, 1 positive, 1 negative, or 1 negative, 1 positive. These are the possibilities. Does that make sense so far? Okay, with that said, I want you to imagine scenarios here. If this was negative and this was positive, is my solution, is my delta G going to be negative or positive? It's not going to be 0. Let's not assume that it is 0. What is my delta G always going to be in this case? It is always going to be negative because I already have a negative subtracted by a positive number. I'm subtracting it by another number. So this is only going to get more negative. So in this scenario here, this is always spontaneous. Okay? So negative, positive. Now with that said, I'm going to go ahead and just erase this. Let's try another scenario. Now let me flip the scenarios on you. This is positive, this is negative. What is happening here? What can I say delta G will always be? And this just requires some basic math. So it's positive value here subtracted by a negative, right? This is subtracted by a negative. So that means I'm adding a positive value. So positive plus another positive. This will essentially never be spontaneous. Okay? To answer your question, yeah, we can have a scenario where it can be positive or negative, depending on the situation. If these are both negative, actually, let's do both positive, okay? What do I want delta G to be? What is my goal here? I want a negative or positive? I want this to be negative, right? So if I have a positive minus another positive, which one of these numbers do I want to be larger? So I want delta H or delta S to be larger. Delta TS. I want this one right here. Oh, so T delta S. I want this to be a larger value. If this is a large value, I'm going to assign the number 10, and this was 5, right? Assuming this is together. So it's essentially 5 minus 10 gives me a negative. Okay, so I want this value right here on the right to be a larger value. And so I can't change what these two values are, the delta H system and the delta H surrounding. But what can I change? What number is flexible here? Or what letter is flexible? Remember, these are usually this is the delta S of the entire system. It's just the entropy. I can't change that. This is just the enthalpy. I can't change that either. It's a number that's already set. But what can I change? Once again, we're assuming that these are both positive. The temperature. So I can increase my temperature. So at higher temperatures, this will be spontaneous. Okay. So if it's both positive, it will be spontaneous at higher temperatures. Okay. At lower temperatures, it could be non-spontaneous. Now, if I flip the scenario, if these are both negative, I don't want this side to be a big number because this is negative minus. I want this one to be the big number. So in this case, I want a lower temperature. So in order to be a negative negative, I want it spontaneous at lower temperatures. Well, it will be spontaneous at lower temperatures. Okay, does that make sense so far? We're going to go through some examples of this in a bit, and there is a table to show you, but for now, I just wanted to get that across so that you could visually see this. We do always want delta G to be negative because that is going to produce a spontaneous reaction. That is our goal. Okay. So with that said, I want you to go ahead and just calculate your delta G value using the information you have been given right here. Okay, let me just draw a line here so you can see it. It's a little bit messy. So you have your delta H, you have your delta S, and then you have your temperature. Tell me what the delta G is for each of these three letters, and then tell me if it is spontaneous or non-spontaneous. I'll give you some time to work on that, and then we will conclude with the poll and some other things.
Professor, just a quick question. What's the units
For which one?
for delta G?
Usually it's kilojoules per mole.
Okay.
Okay.
Right, thank you.
Okay, so let's talk about this. For the very first one, what did everyone get for A? What is your value for delta G? It shouldn't be negative 1,475. Anyone else get a different number? Also not negative 125. So let's set up the equation here, okay? I have delta G is equal to delta H minus T delta S. Okay. So with that said, if this is positive and this is positive, right? This can be either, the answer could be positive or negative depending on what my temperature is. Something I want to point out though, what unit is this? And what unit is this? So you want to make sure you convert it to the same units, okay? So the answer should have been 24,000 joules or 24 kilojoules. And if you roll 23.5, it's about the same. All right, and this is a positive value. So is this spontaneous or non-spontaneous? Okay, it is non-spontaneous. Now I want you to do the same thing for the other two. If you've done it, you can go ahead and just type in the chat what your answer is. If you haven't done it, make sure your units are correct. Okay, so let's plug in your numbers, okay? For delta H, why don't I change that into kilojoules? Oh, sorry, into joules. So this is essentially 25,000 joules. Okay, I am going to subtract 25,000 joules from something. That something is going to be the temperature, which is 300 times the delta S. The delta S happens to be 5. So what does this come out to? This is about 1,500, okay? So 25,000 minus 1,500 gives you about 23.5, give or take, okay? Does that make sense? The person who couldn't figure out the first one. Okay, for the second one, the answer should have been negative 5,000 joules. If you wrote this in kilojoules, negative 5 kilojoules. And remember, make sure your units are converted correctly. Okay, so this one is spontaneous because it is negative. What about our last one? Not negative 2,490. Anyone else? So negative 11,490. Again, joules, you can also write this as 11.49 kilojoules. Okay, and this one is also spontaneous. Now, if you're having trouble with the calculations, make sure you convert your units to the right number. If you're entering this into a calculator, solve for this part first so that the minus doesn't mess you up on stuff, okay? It's a number here minus whatever this number is when you solve it. Okay, does anyone else need time to copy down any of these answers before I clear the screen? Okay. So we're gonna come back to this slide. We're gonna pick up from this part here. For now, I'm gonna go ahead and give you the polls. For those that are co-hosts, you can go ahead and stop recording. Okay. So you should see the poll now. There is a total of 4 questions. As you are working on this, I do want to bring something up. For those of you that are missing more than one homework objective, in other words, in ALEKS, if you're missing more than one homework's worth, right? So like one objective's worth, same thing with Connect, if you're missing more than one, and your quiz grades are lower than 60, I strongly recommend considering dropping, because that's going to hurt your grade a lot. Once again, if you're missing more than one objective on either homeworks, right? Because we so far we've done what, like 6 homeworks, 7 homeworks, right? Objective wise. If you're missing more than one of those, if you're missing like 2 of those, essentially you're missing a third of your homework so far. Okay. and you are scoring below a 60. So all three of these categories, you're not doing well in homeworks and either homeworks. And if you are scoring poorly in your quizzes, and that's across the board, getting lower than 60, then I strongly recommend dropping. Okay. Now, if you are doing great on your homeworks, you're doing 100% all the way across, and even if you're getting 60s on quizzes, that's still okay because your grades are still going to survive and your grades are still going to be good. But if you're struggling with homeworks already and you're getting below 60s, your grade's going to hurt a lot. And some of you may not pass. So for those people, I strongly recommend dropping. Okay. No, there's nothing you can do about the grades that already submitted. That's just the grade that's there.
Do you drop the lowest quiz grade?
I dropped the lowest quiz grade, just one of them.
Quiz today, there are questions with multiple steps. Are you going to go over and give points for the steps we get right in case we mess
If I
one up?
can, yeah, I have that set up in a particular way. If I can find out where it is, then I will give you points for it.
Amazing. Thank you.
To answer your question, Edwin, I don't like to answer what if questions. One of the reasons why I don't like to answer what if questions is I always get that famous line of, oh, if I'm failing everything right now, but if I pass the final, would you pass me? That is a very big what if question. Your final is only worth 20% of your grade. I'm not going to curve anything like that. Whatever you get on the final, it counts for 20% of your grade. That's how it is. And same thing works here. If you're doing great on the homeworks and quizzes, you should do great on the final. But if you just have one bad day, you bomb the final, let's say you don't do well on it, it's only worth 20% of your grade until you get a 50 on it, right? You're still getting 10 out of your 20 points. In most cases, the department will make the final. Since we are meeting in person, it's probably going to be one of the ACS exams that they have. If not, then I will have a final ready. The final exam is in person, yes.
And it's cumulative or no?
It is cumulative. It's of the entire thing. I believe it should be the last day that we are scheduled to meet. I will get a confirmation from them. It's definitely in December. I'm not sure if it's the 14th or the 21st. It's one of those days. And then we're meeting at 4 o'clock usually. Yes, just Chem 2. Although you do need to know some Chem 1 in order to answer stuff. Okay. ACS is the American Chemical Society. Okay, so I'm going to give you another one or well, say 2 more minutes for the poll, and then I'm going to close the poll.
Hi, Professor. I can't
Yep.
see the poll.
You can't see the poll? On the very bottom, you click the word, click on polls, you should see it. If you don't see that, you can click on the 3 dots for more, and it should show up a poll.
Okay, got it. Thank you so much.
And for anyone who is messaging me directly, I can sit down with you during office hours and we can go over a calculation of your grade. I assume most of you know how to calculate your grades and you can see all your grades already, but if you don't, I will gladly sit there with you on that. But again, it will just be for what you have already done. I can't guarantee how you will do for the future quizzes, for the future homeworks, and for the final exam. Okay. So once again, a lot of the what if questions, this is always hypothetical. You could say like, I'm going to go get 100 on the final exam. But then if you don't get it, then what does that say about the grade? You know, so I can calculate a grade with 100, or I can calculate a grade with a 0, and then any number in between that if you want. But that's not going to get you a guarantee of what it is. Okay. Again, for all the people sending me private messages, I will try to answer all of those as fast as I can in office hours if you bring it there. Okay. So I'm going to go ahead and close the poll in about 30 more seconds. There are no extra credit quizzes. I already dropped a quiz grade. And I don't know if you would want my extra credit quiz. It may be very difficult. So you may end up scoring no points on it. Okay, so I'm going to give you about 10 more seconds for the poll, then I'm going to close the poll and we'll go forward from there. Okay. All right, I'm going to go ahead and close the poll now. So let's take a look. Equivalence point is essentially just moles of acid equal moles of base. When a precipitate forms is when QSP is greater than KSP. Number 3, titrations, when it produces a pH greater than 7. Greater than 7 usually is a weak acid strong base titration, because the weak acid, all that's left after that, if the equivalence point, is going to be your conjugate base, which is a base nonetheless. And then for the last one, I see a lot of people struggle with quizzes. Some of you struggle with Alex. One person seems to have no issues whatsoever. Okay. All right. With that said, I'm going to transition over into office hours. So it should be ready somewhere around like 6:35 or 6:30, give or take. So other than that, enjoy your day. I'll see you all next week. Okay. And if you have questions, come to office hours. If you missed one poll, it's very minor. I won't count it against you that much. Generally speaking, if you're missing like 4, 5, 6 polls, then it's kind of showing that you're not there. Okay. Missing one poll is very minor. All right. I'm going to end the meeting now. I will see you all in office hours.